Another parameter that is sometimes used in EEG are the Yorth parameters. These are not as widely used as some of the others. You don't see a whole lot of publications with these, but they're interesting. The reason they're interesting is they use they're basically statistical moments and ratios of statistical moments. But what they give physically is they give measures of what the signal looks like in the time domain. So some of them will give a measure of how close, for example, to sinusoidal a signal is. Others will give a quantification of how peaky the signal is, or how much the signal deviates from sinusoidal. So they're interesting in that they provide, first of all, measures in the time domain, and secondly, measures that we don't get necessarily from other parameters. So they're essentially the statistical moments. This is an example of a statistical moment, the nth moment. C is the mean. You can see that there are 3 Yorth parameters used in EEG: activity, mobility, and complexity. The mobility describes like a mean frequency. It's the ratio of the second moment, which in this case would be standard deviation, to the mean or average power. You can see the complexity is the ratio of the fourth to second moment over the second to 0th moment. So they're just interesting because they do give some indication of the shape of the EEG in the time domain. And there aren't very many other. The wavelet transform, which we'll talk about shortly, sort of does that, but not quite in the same way. So anyway, the Yorth parameters, they were introduced in the mid-1990s. You do occasionally see some publications tend to be used a little more often for a spontaneous or event-related kind of EEG. A little more oftenly used for just the sort of baseline EEG that's not task-oriented, because it does tend to do like an overall characterization of the signal. Okay, wavelets. So part of the issue with analyzing the EEG is, as we've discussed before, the EEG is in general non-stationary, meaning it does evolve over time. Even resting state, eyes closed EEG has some non-stationary or temporal aspects to it. So because of this, there are a number of methods that are both time and frequency based methods. And the easiest method is the spectrogram. The spectrogram is a classic technique used in signal processing. You basically take a Fourier transform and look at the spectrum over a window of your signal. And then you slide the window over and you look at the spectrum again. You can and should have overlap between the windows. And so you do get an indication for how the spectrum varies over time. The main limit of the spectrogram is that your choice of window length really is going to determine your resolution. So obviously, if you pick a very, very short window length, you're going to get very good indications of how the spectrum changes as a function of time, because your window length is very short. On the other hand, if you have slowly varying components or low frequency components and your window length is too short, then you will lose those low frequency components. So that's the main disadvantage of using the spectrogram. So because of that, wavelet techniques were applied or have been applied for time frequency analysis. And what makes a wavelet different is that at frequencies where you have slow variations, or close to DC type portions of the spectrum, you can choose a long window, and then in regions where you have high frequency variations, you can choose a very short window. So you basically change the window length according to what scale or what frequency you're looking at. So what is a wavelet? A wavelet is a function, and we essentially use the wavelet function as our basis function for a transform. When you take a Fourier transform, your basis functions or your transform functions are essentially sine and cosine functions. When we take a wavelet transform, our basis functions are our wavelet functions. So there are a number of different ones. Which one you use depends on the application. For EEG, there have been a number of different wavelet functions that have been used. So here is a comparison of what we're talking about, comparing the wavelet transform and the short time Fourier transform. So the figure on the left here, well, first of all, the figure at the bottom indicates that for the spectrogram or the short time Fourier transform, we basically are taking our data and we're dividing it into a series of windows, and then we get a fixed frequency resolution at each window. For the wavelet transform at low frequencies, we choose a long window. At higher frequencies, we choose shorter and shorter windows, meaning we're going to get better frequency resolution, or we're going to get a broader or broadening of our frequency, or less frequency resolution for the short windows, greater or finer frequency resolution for our long time windows, but less indication of how that changes or evolves over time. So these two figures just give an example. The classic, if you want to look at non-stationary signals, the classic non-stationary signal is the chirp. In this example, the chirp signal is going from 1 to 110 hertz, and we are just looking here at the short time Fourier transform and the wavelet analysis. And so what you can see is on the short time Fourier transform, there's lots of poor resolution. You don't get a clearly defined indication of how the spectrum changes with time. There's going to be lots of broadening of that signal. If you look, however, at the wavelet analysis, you can actually see the shape of the chirp. You can see the frequency content evolving in time from lower frequency up to higher frequency. There's some broadening here as well, but not nearly as much as what we see with the short time Fourier transform, which you can hardly even tell what you're looking at. So this is a more definitive example of what a wavelet looks like. This is an example of a typical, what is called mother wavelet function. The mother wavelet function would be like the fundamental frequency in a Fourier series. So it's sort of like the function that hasn't been shifted or scaled. And so what you're really doing is you're taking this little function and you're really finding the correlation between this function and your signal. So that's what's indicated here. This is like a correlation integral where you're trying, and so what comes out of that is how similar at a given time is your data to this mother wavelet. So obviously if they're highly similar and highly correlated, then you're going to get high values. If they're not highly similar and not highly correlated, you're going to get smaller values. So you take this mother wavelet and you do this correlation, and then what you do is you do what's called scaling the mother wavelet. So you might take this and make it skinnier, where you sort of squish it all together. What that would do is that would pick up obviously higher frequency components in your data. So the mother wavelet gets scaled over really, in this case where this is what we refer to as a continuous wavelet transform, the user determines how many scales to use. And these scales correspond to frequencies. And in MATLAB, there's a very convenient function called scale to freq that will tell you for a given wavelet and a given sampling rate for a certain wavelet scale, what frequencies does that correspond to? And it does correspond to a range, and the ranges do overlap. So, for example, if we look over here at scale 14 and scale 12, there would be a frequency range in hertz that corresponds to, and I'll just pull some numbers out of my head, completely arbitrary. Let's suppose that scale 12 corresponded to 8 to 12 hertz. Scale 14 then might correspond to 6 to 10 hertz. So there's some overlap. That's known as redundancy, and that's one of the issues with the wavelet transform, is that from scale to scale you're not necessarily getting unique information. So this is what a wavelet transform looks like, where you're basically doing a 3D plot without the third dimension, which is now in color. So you've got scale versus time, and you can see the intensities. This one clearly has some almost oscillatory behavior. So that's the wavelet transform. We'll look at one other figure, just talking about choice of wavelets. This is just an example of a chirp signal where we've used 3 different kinds of wavelets. You can see the mother wavelet functions illustrated here. You can see that when we use this wavelet known as the HAR, see we get a lot of ripples here in our output, indicating that there are some issues with harmonics of this wavelet showing up where they really shouldn't be showing up. So different wavelets will give better output. In this case, obviously this COIF 5. You can see really clearly, you can see the shape of that chirp. You don't get a lot of garbage out here where you know there's no signal, and that's a good sign. So once again, wavelets widely used to give you time, frequency information scaled appropriately.